Introduce Binyamini. Oh, thank you. Started recording. And he'll speak about tameness in geometry and arithmetic beyond o-minimality.
Okay, thank you very much. Yeah, so thanks the workshop organizers for inviting me. Yeah, obviously this is not how we wanted. I'm speaking also as one of the program organizers, so it's not exactly how we wanted to start off our program with this Zoom stuff. But okay, nothing to do. But I just wanted to say that I was one of the junior members in the previous workshop 13 years ago, and it was a great experience for me, and it's kind of the first time that I heard of o-minimality, and I probably wouldn't have heard of it otherwise. And I remember it was also very good socially, to interact with people, and that aspect of it is kind of lost now, at least for those of us who are not in fields. So I just want to encourage everybody to kind of contact me, or I'm sure the other participants agree. Like if you have questions, you want to email me or Zoom chat me, and let's try to make it as if we are all in Toronto, at least until it's possible. Okay, so I'll start with my talk. I noticed after I submitted my title and abstract to Chris that it's kind of nearly identical to another talk, to the talk by Philip, but it will be something completely different. So so this word beyond in mathematics, it can go in various directions, but maybe by the end it will seem still connected somehow. Okay, so let me start. So okay, so Tame geometry is it was in some sense envisioned by Grothendieck, and well, he has this quote. Once I was giving this talk in a seminar in Paris, and I think Ofer Gabor complained that I'm giving an English translation. It ruins the original, but that's the best I can do. So Grothendieck said that after 10 years, I would now say with hindsight that general topology was developed by analysts, and in order to meet the needs of analysis, not for topology per se. And so Grothendieck was like envisioning some kind of theory that would be more suitable for the type of phenomenon that we see in geometry and in topology of a more tame kind. And o-minimality is kind of one candidate, a very good candidate for realizing this this vision. So let me kind of mention a few good things about o-minimality that make it really like a suitable candidate. So first of all, it meets many of the criteria that were suggested by Grothendieck. So for example, it allows for stratification into smooth spaces and triangulation. So if you have any set that is definable in an o-minimal structure, then you can stratify it. You can write it as a union of smooth strata, and you can triangulate it in the sense of simplicial topology. It also contains, okay, so on one hand, it's rich enough to allow for these operations. On the other hand, it really contains a lot of things. So for instance, it contains the types of spaces that Grothendieck was probably thinking about, like moduli spaces of algebraic curves, moduli spaces of abelian varieties. And more recently, it was shown that in some deep sense, it contains also the period maps for variations of Hod structures. So it really contains a lot of the kind of things that we get in, when we do algebraic geometry and those kind of things. And also we already know that it is kind of connected to arithmetic geometry because it's had a big impact. So when I will talk about where this impact came from, the Pila-Wilke theorem, but then after this theorem, which is a theorem purely in Tame geometry, was proven, it was used for many other things by Pila and Zannier and many other people. So I will try to give a brief introduction to what is this impact and how it works in some simple cases and what's left to be done after this. Okay, and like the motto of my talk, the thing that I want to convince you of is that, so as topology wasn't really developed with like geometric topology in mind, it was developed for the needs of analysis. O-minimality wasn't really developed with these needs of arithmetic geometry in mind. So it was developed with real geometry in mind. So it was generalizing some phenomenon that existed in real geometry, like a sub-analytic geometry, and you can say sub-exponential geometry. People, I mean, when it was formulated, it wasn't with this type of arithmetic geometry applications in mind. And I think that if we want to go further in the arithmetic geometric directions, then we might need to refine our foundations a little bit. And that's what I will try to talk about. Okay, but let me start by just explaining how it started. So how this Tame geometry came to be related to arithmetic geometry and how it works in practice. So I'll denote in this talk by xgh, where x is a set of subset of Rn. It will be the points that have degree g, Galois degree. So they generate a number field of degree g over q, and they have height h. So I mean, for most of what I will say, I will take g is equal to 1, and then I mean, this just means that we are looking at rational points, and then this height is the standard height on rational numbers, so the maximum of the numerator and denominator. Usually people will just denote this by xqh. So for some of the things that I will talk about, it will be convenient to consider like a bigger g here. So looking at points that are not rational, but generate a number field of some bigger degree. So that's why I include this in the notation. So in case you're not familiar with this particular notation. Okay, so this story about the connection to arithmetic geometry, you can say it started with this Pila-Wilke theorem, a very famous theorem that I'm sure many of you might have heard, but I repeat it just in case. So the theorem is as follows. You take a set A, which is definable in an o-minima structure. And what we are interested in is counting the rational points, or you could say algebraic points of some fixed degree or something like that. And the theorem says that the number of rational points is sub-exponential in the height. So it's less than h to the epsilon for any positive epsilon, with a caveat. So we cannot count in the whole set. If we take an algebraic set, like the curve x is equal to y inside R2, then this will have many rational points on it. Whenever x is rational, y will be rational because y is equal to x. And there are many rational numbers of a given height, something like h squared. So it will definitely be false for this kind of context. So we have to throw out the algebraic curves. So A-alg is just the union of all the connected semi-algebraic curves inside the set. We throw them out. I warn you that this guy might not even be definable. Okay? So this is just a set. It's the union of all the semi-algebraic curves in A. We throw out this set. We are left with what is called the transcendental part. And this is what the Pila-Wilke theorem talks about. We're counting points in the transcendental part, fixed degree, as a function of height, and it's going to be less than some constant, asymptotic notation, depending on A, on the degree of the points, and on this epsilon that we chose, times h to the epsilon. So it turns out that o-minimal sets, even though o-minimality was invented for geometry, they are in some sense tame from the point of view of arithmetic geometry. So if you are looking at a set which is geometrically tame, so it's in an o-minima structure, then there is some natural abstraction in the form of containing algebraic curves. And if you don't have this natural abstraction, then you have some bound on the number of rational points. So it shows that some good behavior for, like some Diophantine good behavior for sets that are definable in o-minima structures. And then this was a starting point of many applications of o-minimality to Diophantine geometry. So I will show one application, kind of the simplest possible application. So it's a theorem of Laurent. It was conjectured by Lang before. So we take an irreducible curve in C star squared. So C star is just C minus the origin. So it's a multiplicative group with respect to products. And we are squaring it. So we are taking kind of two copies and we take some curve in there. And we suppose that this curve is not a coset of a subgroup. So there are subgroups like x is equal to y or x is equal to y squared. These would be multiplicative subgroups, and we are assuming that we are not any coset of any multiplicative subgroup. And then this theorem of Laurent, conjecture of Lang, says that V should contain finitely many torsion points. So torsion point here would just be a couple of roots of unity. So some point that when you raise it to some power, it will be the identity. So it's just two coordinates should be roots of unity. And let me show you the idea for how to prove this. I mean, the general strategy is by Zannier, and maybe some ideas they're already due to Sarnak. So the idea is as follows: where does o-minimality, where do transcendental things come into this completely algebraic problem? So we start by uniformizing the C star. And in fact, for me, I don't really need to uniformize all of C star, because we are interested in the roots of unity in C star. So basically, all these points that we are interested in, they will lie on the product of the unit circles inside C star. So I'll kind of uniformize only that part, and I take a map from 0, 1 squared to C star squared given by just these exponentials. So it just parameterizes the unit circle in each coordinate separately. Okay, so this is a nice map. It's, for example, it's analytic on 0, 1, so it will be a definable map in 0, 1 square in Rn. I mean, this restricted to this compact 0, 1 square, it will be definable in R sub n. And then I let X be the pre-image. Okay, so X, this is my set that lives in some O-minimal structure, in Rn in this case. And you can see that X contains no semi-algebraic curves, unless you had a subgroup here. So if you have a subgroup, it will be exactly a curve. So let's say you had something like y is equal to x squared, then this will turn into t is equal to 2s or something, right? We're just uniformizing by taking logs. So you can check, in this case, it's not very hard to check that if you are not a coset of a subgroup, then you will not have semi-algebraic curves inside this X. That is what is usually called the functional transcendence statement. So we are asking if there can be some semi-algebraic thing. So if we think about it as a function of a parameter, we are asking, is there some algebraic function in there, like an algebraic function of a time parameter? And functional transcendence says that, okay, some types of sets cannot contain such algebraic function. Okay, and then if we know that it's a definable set and no semi-algebraic curves, P-lawilty tells us how many rational points will be in there. Okay, so there will be like well, I'm looking at rational points of degree 1 of height h, it will be h to the epsilon for any positive epsilon. For example, for epsilon equal to 1/3. Now, on the other hand, let's take a torsion point. Suppose that you have a torsion point in there, PQ. So it will be pi of something, S and T. Suppose that it's a torsion point. And let's write H for the height of this S and T. So that's a point in X. S and T belong to X. They're in the pi inverse of V. And the point is that the order of these roots of unity is roughly the height. I mean, right, when you are using this kind of map, if you plug in a t here, which is a rational number with denominator n, it will be a root of unity of order n. Okay, so this height is roughly the order of the roots of unity. And now there is some very classical theory, maybe to Gauss, I guess, that says that the roots of unity, the number of their Galois conjugates is, I mean, it's almost like their order. So certainly it's more than, say, the square root of their order. Basically, all the primitive roots of unity of the same order are conjugate to each other. So it's not a trivial statement. It's a statement that is cyclotomic polynomials are irreducible. And so you can try to think of a proof. It's not so easy. It's easy after you see how Gauss did it. It's not a trivial statement. So this is what is called the Galois lower bound. So we have our roots of unity, and for some reason we know that they have many conjugates, I mean, as a function of their order. Now every root of every one of these conjugates will be a point in x1h, okay? Because V was Well, in fact, I didn't say V is defined over a number of fields, but let's assume for simplicity that V is defined over Q. Otherwise, you need some very minor modifications. But suppose for simplicity that V is defined over Q, then all of the Galois conjugates of this root of unity are also going to belong to V. So as soon as we have one, we have all of its conjugates also in there, and there's h to the 1/2 of them. Okay, so this number of points in X1H, that's the roots of unity of order H, should be at least h to the 1/2. And then we get a contradiction. On the one hand, it should be less than h to the 1/3, and on the other hand, it should be more than h to the 1/2. So once this order of unity, or I mean, the height of these primitives is big enough, it's just a contradiction. So you cannot contain any roots of unity once the height is bigger than something. And that means that you can contain only finitely many. And you can even, if you knew these constants, then you could even say how many. So, okay, so that is the kind of the rough idea, and it was later used for many other things. I mean, it was never used, I guess, for this particular case. It was used by Pila and Zannier for proving Manin-Mumford, which is a similar statement about abelian varieties, and later it was used by Pila for proving the under-odd conjecture, for modular curves, and many other things. So, in general, if you want to use this theorem, it works when you have these lower bounds. I mean, if you look at this statement, that there was some Tame geometry part. I mean, up to this point of the Pila-Wilke theorem, and then we had to contrast it with some other part, with getting a lower bound for the Galois orbits. And this part we have to get from somewhere. Like here, we got it from this theory of cyclotomic polynomials. So, for example, if you want to do Manin-Mumford, what Pila and Zannier did, then you need to know that if you have an abelian variety and an n torsion point in it, the number of Galois conjugates is bigger than a constant times the order. Okay, it's exactly like these roots of unity. I said that the number of Galois conjugates of a root of unity is more than n to the 1/2, for example. So you need something like that if you want to prove Manin-Mumford. And if you want to prove things about the under-odd conjecture, then you need, never mind if you don't know what it is, but just schematically, you have some points that you are interested in counting, checking that there are finitely many of them. You need to know that the number of Galois conjugates is bigger than a constant times some parameter associated to this point. In the case of Shimura varieties that are moduli spaces of abelian variety, this thing will be the discriminant of this CM ring, the ring that measures all the endomorphisms of your abelian variety. But I mean, you don't need to know this kind of Shimura stuff to follow the rest of the talk. I just want to show that, I mean, 1/2 of the strategy is always the same, and the other half, it depends on the context. You need to get these Galois lower bounds. So, and the proof of the Galois lower bounds, they are quite similar to the proof of Pila-Wilke. So they are based, both of these are in some level based on what are called transcendence methods. And transcendence methods, these are kind of methods that come to Diophantine geometry from transcendental number theory, where you are constructing some auxiliary polynomials and they have to vanish on algebraic points. Okay, so you have polynomials. On the one hand, they are very nice analytic functions. They are just the nicest possible analytic functions, polynomials. On the other hand, they interact nicely with algebraic numbers. Okay, so if you plug in an algebraic number into a polynomial and you know the height of the coefficients, then you can estimate how small the result can be. So that kind of thing, unless it is 0. So I mean, polynomials have this dual purpose. I mean, on the one hand, they belong to the algebraic world. They play nicely with integers or with rational numbers or with algebraic numbers. And on the other hand, they are very nice analytic things. So for example, they live in the o-minimal, in any o-minimal structure, you have these polynomials, you have their 0 loci, so you can look at their zeros. These are very kind of analytically tame things. And it's this interaction between the two roles of polynomials that allows us to prove these kinds of statements. And I mean, it almost seems as if Pila-Wilke and these proofs are working similarly. So the only problem is that Pila-Wilky is quite unique among these transcendental methods in that you only use polynomials of some fixed degree. So in the proof of Pila-Wilky, you construct auxiliary polynomials, but their degree depends on epsilon. It doesn't depend on h, for example. So in all of the other transcendence methods that I know about, the degree of these polynomials will depend on h. So if you look at things like the Wustholz analytic subgroup theorem or Masser-Wustholz isogeny estimates, you will use polynomials of degree that's roughly like log of the height of whatever thing you're interested in. And if you look at even more classical things like a Schneider-Lang theorem, it's a very classical theorem in transcendence, it will be even linear in h. So you will use some polynomials that have a degree roughly like h. But in Pila-Wilky, there's no dependence on h. You're using polynomials depending only on epsilon, for example. And that's what makes it so general. I mean, that's why you can prove Pila-Wilky in this vast generality of o-minimal structures, and you can't really hope, at least not with the methods that we know, to get results like 3 or 4 with these methods. They really require you to use polynomials depending on h, and you have to analyze more delicately how things depend on the degrees of polynomials. Okay, so as I said, in general, you cannot expect to improve this. So, I mean, because of the great generality of the Pila-Wilky theorem, you can construct examples where you have almost h to the epsilon. So these constructions will be some kind of lacunary functions or something like you can build with your hand functions that will have many rational points of a given height, but they wouldn't be very nice functions. I mean, they could be analytic, restricted analytic, but they wouldn't be something like an elliptic function and a Billian function. That's exactly what I'm saying here. So here, for these things, both of these transcendence methods, in fact, most transcendence methods, they apply to elliptic functions or abelian functions. So these are very nice functions. We know a lot about them. They satisfy differential equations. They have finite order growth at infinity, all kinds of things. So when you have much nicer functions, you expect something better. And Wilky made the conjecture that if you have very nice functions, so let's say you start with a set that's definable using only the exponential function, plus, I mean, algebraic thing. So R sub x, the structure generated by the exponential function and the real field, then we should get a much better bound. So we should get that if we count the number of points of degree g and height h, it will be a polynomial depending on the set in g and log h. So I'll make a few remarks. First of all, that wasn't exactly the conjecture. The conjecture was probably for g is equal to 1 here. So when you start to look at how the proof works, it's kind of natural to generalize his conjecture to this. So I mean, in these proofs, the degree and the log of the height, they play roughly the same role. So if you can get something polynomial in the log height, you will probably also get polynomial in the degree. And so I'm slightly generalizing the original one. And so this was a conjecture. It was in the original paper where they formulated their, where the Pila-Wilky theorem was formulated, the Wilky also formulated this conjecture. And a few years ago, Harry Schmidt noticed the following fact. He made the following discovery, that if you can prove this, not just for Rx, but for some large structure, then this Galois orbit's lower bound will follow. I mean, the ones that, so this would follow for abelian varieties, and this would follow, and possibly others. So there is a way to get the lower bounds themselves from the point counting, but you need this kind of sharper version of it. So let me show you again for this baby case with roots of unity, how it works. It's very simple in this case. So suppose you have a root of unity of order n, and G will be the order. G is the number of Galois conjugates. So our goal is to show that G is big. G is some power of n. Okay, so the idea of Harry was to look at the graph of this exponential map. Okay, and on this map, I claim that every torsion point gives us such a G endpoint. So what it means, let's look at P, for example. So we have P, it corresponds to some point on the graph where, okay, in C star it's P, so it's a point of degree G. The height of P itself, because it's a root of unity, it's in fact 1, it's bounded. And on upstairs, I mean, if you look at the coordinate sitting here on the graph, then this will be just a rational number. Okay, so it will be degree 1 upstairs, rational, it will have height n. So eventually this pair, I mean, the thing that sits on the graph is a point of degree G and height n. But we get not just one point, because if P is on the graph, then every power of P is also on the graph. And all these powers are different if P has order n. And okay, they are all roots of unity of the same order. So for the same reason, they are all G endpoints. So we get a bunch of these G endpoints. We get n points of degree G and order n. And then if you have this nice counting, you will know that n is bounded by this number, which, as we said, should be a polynomial in G and log n. And now this is a very common trick in transcendental number theory. Whenever you have such a bound, you can just forget about the log n. I mean, log n is so small compared to n that you get some power of log n here, it means nothing. So eventually, n is bounded by a polynomial in G. And that is what we wanted to prove. Okay, so n is less than some power of G, so G is bigger than some power of n. So in this way, you can get the Galois orbit lower bound, and it works almost exactly the same way for abelian varieties, for example, and even for this Shimura case. And I will say maybe a little bit more about it toward the end. Okay, so this was if this conjecture holds. But as we said, it doesn't hold for all o-minima structures. So I want to formulate some kind of general theory where we could expect this to hold. Okay, so what would be a reasonable set of assumptions?
But God, sorry, God.
Yeah.
Didn't you need the complex exponential before, not the real exponential?
Well, here it's the complex exponential, yeah. I mean, but restricted. So you need really.
But the conjecture is about real exponential.
Yeah, I mean, this conjecture is about real exponential, but I mean, so Schmidt's kind of discovery was that if it holds for some large enough structure, not for Rx, but I mean, suppose that it holds for a very rich structure.
Okay, sorry, I didn't see that. Thanks.
Yeah,
yes.
So I mean, definitely, I mean, this Wilke's conjecture, it was stated for Rx because Alex Wilke is very fond of Rx, I guess. But I mean, I'm sure that, you know, he naturally could have made it for other natural structures. Just this is a very famous structure that Alex Wilke knows much about. So it was like a natural first thing to conjecture, but for the same reasons you would expect this to hold for a lot of natural structures. So I want to say what a natural structure would be. So what would we need in order to hope to get this kind of stronger statement? Okay, so I'm thinking about an o-minima structure like a collection of definable sets, and I want to introduce a double increasing filtration on it. So I mean that X will be a union of subsets XFD. So this F I call the format, and D I call the degree, and it's increasing with each of them. So if you increase the degree, you get a larger set, and if you increase the format, you get a larger set. Eventually, you get the whole structure. So every set has some format and degree. Okay, and now I call a set sharply o-minimal if some axioms hold for this filtration. So let me just go through the axiom. So I want unions to keep the same format. So if I take a union like of a bunch of sets AJ, then the degree should be this D, which is the sum of the DJ. So when you take a union, you just sum the degrees. So when I say it has format F and degree D, I mean it belongs to this set X FD for the given format and degree. Intersections have format one time bigger and the same degree. I mean, here maybe you could also allow one time bigger for union. It's there's a little bit of leverage here, but I think that this is the correct notion. So when you take unions, you don't increase the format. When you take intersections, you increase the format by 1. Degree is again the sum. And when you take complements and projections, again, you increase the format by 1. And okay, you don't change the degree. I could have written dj here, in fact, because it depends only on aj. Okay, so that is kind of the Boolean algebra part of the filtration. Okay, so whenever you have a Boolean algebra, I mean, you could make this definition with any structure, really, any structure of first order logic. So all minimal structures, they have, I mean, they somehow interact with the real field. So for the interaction with the real field, I add the following axiom. So in an o-minimal structure, you have every algebraic hypersurface, for instance. Every polynomial, you can take its zero locus. I'm saying that the zero loci of polynomials of degree d should have, I mean, format n, where n is the dimension, and degree, same as the degree of the polynomial. Okay, so it agrees with the thing that we naturally expect when you are thinking just about the algebraic structure. And finally, the last axiom of o-minimality is that subset of R have finitely many connected components. And to make kind of a sharper analog, I want to add an assumption that, or an axiom, that the number of connected components of such a subset of R should be some polynomial depending on the format in the degree. So it's d to some power. The power depends on the format of your set. Okay, these are the axioms. Each of them is kind of some kind of more effective analog of one of the axioms of o-minimality. And I want to kind of convince you that this is a good extension of o-minimality to think about if you want to think about applications to Diophantine geometry and arithmetic, and maybe in general. I mean, applications to Diophantine geometry are one kind of aspect of it, but this can be used for other things as well. So I want to motivate this a little bit. So first of all, I want to say that one of the origins of o-minimality, it's this theory of Khovansky, what is called the theory of eunomials or theory of Pfaffian functions. It has this flavor for systems of equations. So, I mean, the theorems of this, Khovansky's main theorem says that if you have a bunch of Pfaffian equations in dimension n and you look at their zero loci, then it will be some polynomial in the degrees, and the exponent depends on the dimension. Okay, so that's where this kind of thing comes from. F, this format is like a dimension, roughly, and we are saying there are some degrees, everything eventually should be a polynomial in the degrees, and the exact polynomial depends on the dimension. In Khovansky, it's like that. The exponent is like a square of the dimension, but that is somehow less crucial in the application. Okay, but I mean, this is for systems of equations. And the question is, what about structures? Why did we never do this for structures? And the answer is, first of all, I mean, it's not that it was never done for structures. People, of course, thought about doing it for structures. So Gabrielov and Vorobyov worked a lot on this kind of in trying to take Khovansky's theory and transfer it to like the first order logic context, working with complexity of definable sets, projection, complements, everything, not just systems of equations. And they almost got a sharply o-minimal structure. Okay, so if you go through their texts, you will see that they define a formatted degree. For them, you know, a sub-Pfaffian set is a projection of some semi-Pfaffian set, and then the format is the dimension of this big semi-Pfaffian thing, and the degree is the degree of the semi-Pfaffian. So basically everything is a projection of something that does not involve quantifiers, and you just take the degree and the dimension up there. That was their notion of format and degree, and they proved theorems about all the operations, all the logical operations, but the complement wasn't good enough. So in the complement, they had a format depending on D and F. So you will notice in my axiom, it's very crucial that the format here, okay, when I make some operation, it's always F or F plus 1. We never entangle the degree into the format. Okay, this is crucial because everything eventually is polynomial in the degree. And I'm not saying anything about how it depends on the format. So if in some step you got the degree into the format, then in the next step, you will not know how things depend on the degree anymore. Okay, so like the crucial aspect here is that we always keep the degree like away from the format. And that was exactly the problem with Gabrielov and Vorobyov's construction for the complement. And it's kind of closely related to cell decomposition, the way you usually do complement and the way that Gabrielov and Vorobyov did complements was through such a theorem of the of cell decomposition. So the question is, if we have some subsets of Rn, let's say they are format F in degree D, is there a cell decomposition where the number of cells, is some polynomial depending on the format of the degree, and each of the cells has a format which is depending only on the original format, and the degree is polynomial. So if you had this, then you would get this, theorem of the complement, and you would get the theorem of projection. And I mean, this is basically what we need. And unfortunately, we don't know the answer to this question. I don't know if it's true for the sharply or minima structures that I defined just now. And I don't know if it's true for the Pfaffian, restricted Pfaffian things that Gabrielov and Vorobyov considered. And I mean, that kind of renders it pointless, in my opinion, because, there's a saying that in category theory, you only introduce categories in order to define functors, and you only introduce functors to define natural transformations. I mean, when you make definitions, you're trying to go somewhere. And with o-minimality, you only introduce o-minimal structures to get cell decomposition. If there's no cell decomposition, then might as well use different axioms. But what we discovered with Vorobyov was that there's a way around it. So in fact, we did it for the case of restricted Pfaffian, you can make a different filtration for this restricted Pfaffian structure. So you choose a different notion of format and degree. And with this, you do get a sharply or minima structures, and you do get cell decomposition. Okay, so this is why I think it's kind of it's useful to work with these filtrations. I mean, in some contexts, it's useful to change the filtration. Maybe a certain filtration doesn't have a good property, like doesn't allow good cell decomposition, but if you just modify the filtration, you will still have a sharply or minima structure with all these axioms, but you will be able to do cell decomposition. So the idea is basically that we don't know how to define connected components. So this new filtration, we will say that whenever we had a set of a certain format and degree, all of the connected components have this format and degree in the new filtration. But it's kind of circular. Then, okay, you added more sets, then maybe now it's harder to do cell decomposition. You have to see that you can make the whole thing work, but in fact it works. So you can build up a different filtration such that it will be sharply or minima with cell decomposition. And my student of Dimitri and myself, Benny Zak, he is now working on generalizing this to all sharply or minima structures. So, I mean, we think it's proved already, but it's not written, that for any sharply or minima structure, you can modify this filtration to get a new sharply or minima structure that does allow cell decomposition. In this sense, I mean, cell decomposition, like is written here, with good bounds on the number of degree of the cells and their format, their complexity. Okay, so first of all, not all structures are sharply or minima. I'm kind of trying to argue that this is the thing that separates the nice structures where we expect something like Wilco's conjecture from some random structures like Rn. So for instance, Rn is not sharply or minima because you can find an analytic gamma that can intersect a polynomial p equal to 0 in more than any polynomial of the degree points. It should just be a very lacunary series. So it will intersect linear things at 2 points, but it will intersect quadratic things in 2 to the 3 points. It will intersect cubic things in 3 to the million points. With a lacunary function, you can easily build such an analytic thing. And then this gamma is supposed to have some fixed format if it's in a sharply or minima structure. But if it has this fixed format, then it should have, I mean, the number of intersections should be bounded by some polynomial in the degree of p points, and we can build a gamma where this doesn't happen. So I would argue that this kind of gamma, while it's a graph for restricted analytic functions, it's perfectly tame for real geometry, it's not really tame for Diophantine geometry. I mean, getting something like this behavior or similarly, getting h to the epsilon points instead of log h points, it's something like a space filling curve. If you think about how your structure interacts with the algebraic numbers. So I'm kind of trying to avoid this kind of phenomenon, and that's what these sharper axioms are meant to do. Okay, so let me introduce some conjectures. One conjecture is that arithmetically interesting functions live in a sharply o-minimal structure. So this is very vague intentionally. I can make it more explicit, but what I mean by arithmetically interesting functions. But for instance, I would say the covering maps of a billion varieties, the covering maps of Shimura varieties, period maps, period integrals in general, these kind of things that come from algebraic geometry are supposed to live, we know that they live in an o-minimal structure, and they're supposed to live in a sharply o-minimal structure. So this one is maybe slightly vague. And another conjecture is that in a sharply o-minimal structure, Wilke's conjecture should hold. And moreover, I mean, you should get a polynomial in the degree of the sets that you're dealing with and G and the log height. I mean, we also say how this polynomial depends on the set A. It's not just some polynomial in A, it's polynomial in the degree depending on the format. I am not sure how, I mean, it's not that I know how to prove this conjecture. We have some cases of it. So if you have something generated by restricted holomorphic functions, then Novikov and I have a proof that probably extends to this context. Currently, it is written only for restricted elementary functions, but I mean, it should extend to this. But I think it's a good conjecture in general as a way of extending Wilke's conjecture. I will say that we have a theorem in preparation with Gareth Jones, Harry Schmidt, and Margaret Thomas. We did it for a restricted Pfaffian, not for this sharply o-minimal. But so the theorem says that if you have a set of a given format and degree, then you get a Pila-Wilke theorem with this kind of effective constant. So so you have a polynomial in the degree of the set, depending on the format and the degree G and epsilon, times h to the epsilon. So it's kind of effectivizing this constant, some existential context that you get in the Pila-Wilke theorem. And again, Ben Isaac is working on doing this for general sharply o-minimal structures. Okay, so I want to move to some applications to kind of explain why I think that the Tame geometers should try to prove such things, why I think it would be a place where Tame geometry can contribute more to the Diophantine geometry. So I start with a couple of examples by Masser and Zannier. One of them is the Pels equation. So we are looking at an equation like this: a square minus d b square is equal to 1. And we try to solve it with polynomials. So in the integers, you can always, I mean, if d was an integer and we are looking for a and b that are integers, this is the Pels equation, and it's always solvable unless d is a perfect square. And the question is, what about polynomials? So Masser and Zannier have, in polynomials, actually, there is an abstraction. I don't want to go deeply into the details of what the abstraction is, but Masser and Zannier were able to kind of pinpoint a geometric abstraction to solving these kinds of equations in polynomials. And what they showed was that this abstraction it has the property that if you look at a family, so now I take a d depending on some extra parameter t, then there is a criterion, and the criterion will tell us if there's some natural geometric criterion. If it's met, then you will have infinitely many t's for which Pels equation is solvable. But unless that special criterion is met, then you will have only finitely many t where the equation is solvable. It's kind of like what we had in the first example. So there was some geometric criterion like having a coset. Like if this curve that we're looking at is a coset, then it maybe will have infinitely many torsion points, but otherwise it will have finitely many. So here's the same kind of thing. There's some natural reason why this thing might be solvable for infinitely many t's, but unless that criterion is met, you expect only finitely many t's. And assuming that the relevant functions, which in this case are elliptic integrals, or elliptic integrals in this case, assuming they are actually belonging to a sharply o-minimal structure, we could prove that you can effectively check this, and this finite set of t's is computable in polynomial time. Okay, so I mean, if you are given this polynomial d, let's say you're given an encoding of all the coefficients of d, let's say it has algebraic coefficient, not complex coefficient, then you can actually ask what are the t's for which the Peltz equation is solvable, and we would be able to show that there is a polynomial time algorithm for this kind of purely Diophantine problem using kind of this o-minimal theory, sharply o-minimal theory. Okay, another example is connected to integration of algebraic functions. So we have an algebraic function like square root of x, and we are asking if it's possible to integrate it in elementary terms. So just write out a formula for it that involves composing algebraic functions and exponentials and logarithms. And when you are given some functions, anyone who went to high school and had exercises to integrate such stupid functions, it's very hard to, you have to just guess. And it's hard to determine if you can really integrate a function like that. But there is a theorem of Risch that says that there is an algorithm that can determine if f is elementarily integrable. Okay, again, you can convert this problem into a certain geometric problem and solve it, like with a computer. But then what about a family? Again, it's similar to the previous one. Suppose now that I have a family of algebraic functions depending on an extra parameter t. Then Masser and Zannier again proved that there is some criterion, quite an elusive criterion. If the criterion is met, then you will have this thing can be integrable for infinitely many t's. But if this criterion is not met, then it will only be integrable for finitely many t's. And then this Risch's algorithm doesn't work. It works for each particular function. But if you have such a family, you can ask, can we find when it is integrable? And again, I haven't carried out the details in this case, but very likely that if the relevant functions, which are now a billion integrals, live in a sharply o-minimal structure, then we would get a polynomial time algorithm that computes all of these t's. Okay, I want to give one more nice example with billiards. So this is by Zannier and Corvaja. So they considered a billiard table, which is elliptic. So you have an ellipse t, and that is your billiard table. So the interior I denote by t circ, and the boundary of the table is partial of t. And the billiard shot means that we are picking some point on the table, and we pick a direction, and we just let it run. And whenever it hits the wall, it bounces off. And they proved, Zannier and Corvaja proved some nice theorems about these kind of elliptic billiard dynamics. So for instance, suppose you choose 2 points inside the table and 1 point on the boundary. And we are trying to make a shot that starts in the first point that you chose. I want this shot to pass through another point and then fall into the third point. So it's like think that you are trying to make a shot that would go through somewhere and continue and eventually fall into the pocket. And what they proved is that there are finitely many such shots. So I mean, you can continuously move the direction, and of course, I mean, it may be that you shoot it and it goes a very long time, then it hits P2, and then it keeps shooting many times, and then it will fall in. So it's not at all trivial to determine which shots will actually eventually pass through P2 and fall into P3. But they show that there are finitely many such shots when you are allowed to choose the direction. And they showed one other similar thing, that if you choose 1 point and you, let's say you want to make 2 shots, one with a certain angle and the other with a certain shifted angle. So we are picking some shift for the angle, and I'm saying, okay, I will shoot one ball in a certain direction that I'm allowed to choose, and the other ball I will rotate by this alpha and shoot it in that direction. And they asked, how often will it happen that both of these eventually return? Both of these orbits will be periodic. And again, they proved that it will happen for finitely many v's. And again, a likely consequence of this sharply or minimal stuff is that you can determine these finite sets of shots. So if everything is algebraic, if you give me algebraic points and the algebraic multiple of pi here, then we will be able to compute how many of these finite things there are, and even maybe compute what they are. Okay, so I just want to show that there are many different types of kind of applications of this to different areas of mathematics. And I will finish with one final slide about Galois lower bounds. So, I mean, the previous things that I showed were just effectivizing existing results. So we have results saying that some things are finite, and I'm saying that, okay, we will get good bounds, we maybe can get computation in polynomial times if we have a sharply or minimal structure. But here I want to talk about a different kind of application. So for Shimura varieties, as I mentioned before, in order to prove the under-Ott conjecture, you need a Galois lower bound, and it's this kind of thing. You want to say that the number of Galois conjugates of a special point is bigger than a constant times some powerful discriminant. And Zimmermann proved this for AG. So Zimmermann proved, he proved under-Ott for AG, and it was basically boiled down modulo known things to proving this. And he used two ingredients. One was a height bound. So he knew, because of average Kolmez, which is a very difficult recent result, that the log height of these special points was bounded. And then he combined this with a transcendence method kind of type argument, which is called the Masser-Zannier isogeny estimate. And using these two things, he was able to get this equation 8. But neither of these things are available for general Shimura varieties. They're available for moduli spaces of a billion varieties. And the reason why Harry Schmidt was kind of really pushing this this new strategy and kind of it got people excited about it was that it seemed that if you had the good counting, polylog counting, you could get rid of this second step. So eventually I got the counting that you need, even though we don't have this conjecture about sharply or minimal structures yet. But for this case, I was able to prove that you do get polylog counting, and I proved the counting that was needed for Schmidt's strategy. And then together with Schmidt and year 5, we showed that this height bound implies the Galois bound. So you can remove this transcendence method type thing that was needed before. And this is based on some polylog counting, similar to what I showed, this idea of Schmidt. So we got the Galois bound, and then really a few months ago, Pila, Shankar, and Zimmermann proved the height bound in general. And then as a consequence of both of these things, they finished the proof of under-Ott for general Shimura varieties. But the proof now, basically the only proof is really based on this kind of polylog counting coming from kind of Tame geometry ideas. So the older transcendence methods don't apply. And I think this kind of shows that you can get really qualitatively different applications when you have these sharper bounds. It's not just about getting better bounds for things that are finite. Sometimes it really produces different type of results. Okay, I see I'm a couple of minutes over time, so I'll finish here. Thank you.
Thank you very much. Let's thank the speaker. And does anyone have any questions?